Right. So welcome everyone, and thank you for coming. It's my pleasure to introduce Michele Filippone from CA in Grenoble. Michele is a collaborator, a good friend that is passing by. He did his PhD in Paris at the NS, then went for postdoc with Pete Brower, then got an Abizione fellowship, very competitive fellowship in Switzerland. He was in Geneva, and he's an expert in quantum dynamics, many-body systems, Zen calculus, many different things. And today he's going to tell us about predicting and observing universal Hall response of strongly interacting fermions. So please.
Thank you so much, Adolfo, Fito, and thank you everybody for being here. I don't want to get too much emotional, but I think that today I'm gonna tell the end of a very long story that started somehow in 2017, where I started doing some prediction indeed concerning the behavior of the Hall response, classical Hall response for strong interacting quantum fermions. We derived some prediction, some universal effect, and that which motivated some experiments that actually came out during the last 2-3 years. And this is a long story with many people that should acknowledge. So there is, of course, the experimental team of Leonardo Fallani at the University of Florence, a cold atom experiment. And on the theory side, I really benefited a lot from many discussion and help from many people. Charles Edouard for what was concerning topological effect, Cécile Perrin and Sebastian Grechner, which helped me out with many of the numerical DMRG simulation that you will see through this talk. And of course, many discussion with Uli Schalwok and Thierry Giammarchi. But before going into detail, I believe to understand that you are much more from a condensed matterish background. You may confirm, yeah. Me too, so you're not alone in this trip. So indeed, my main aim today is to bring you through this story, and I think all the message is essentially here, that there are some condensed matter physically motivated question, namely the behavior of a Hall bar. Some people may find it boring. I will try to somehow go deeper in some wondrous aspect actually of the Hall response of methods. And indeed, I think that I shouldn't introduce this device here. This is a Hall bar. What you do in condensed matter all the time, essentially, when you don't know something about the conductor, you do two things. The first, you see if it conducts, so you establish whether it is a conductor or not. And then maybe you want to know about how many carriers carry this current, okay? This is very important. If it is low density, it will be strongly correlated, and so on and so forth. So how you do that, you drive a current to the system, you apply a magnetic field, and you measure this sort of bias voltage, which is transversal to the conduction transport, okay? There are some open questions about it. I will go through them. And I think that for the first time, we came out with a sort of minimal experiment which would highlight universal effect of strong correlation on many body fermions, on many fermions in such a system, in the most minimal setup ever, where you could really start exploring this physics. And I think, meaning my main aim here today is to let you understand actually what this picture is telling to you, okay? And how it works differently. So we implemented, just to agree on what we see altogether, we see two one-dimensional systems which are coupled to each other. What I will be able to do, and this also highlights the difference of how you can investigate all physics with a sort of a neutral atom quantum simulator and an actual condensed matter system, is not that you have, here in this case, what you have got huge chunks of metals that you attach to the system and you can drive a current through it. Here, the protocol will be different. For instance, I just prepare a system at equilibrium, so I just prepare a sort of gas. I tilt it, and then just because of gravity, essentially, this is just equivalent to apply an electric field, and then current will flow in the system. I can measure the current because I can essentially measure the momentum distribution of all the particles on the gas. So indeed, here you see, I hope you see well enough, there is some contrast between negative and positive momentum. So my gas has got speed, has got current, so I can reconstruct the current in the system. And I think the most difficult part, so the one which is unused, is the fact how can I introduce essentially a gauge field which coupled to neutral matter, neutral matter is not charged. So I cannot do a synthetic magnetic fluxes. And how can I measure indeed the proxies of the Hall effect, which are not voltages, but actually differences of particle polarization? The size of these balls here is just to represent the fact that because I've got a current and because I have got the Hall effect, what we do expect that essentially synchrotron motion particle will start essentially curving, okay? And charge the system transversally. So the size of these green balls, if you want, is just the amount of particles that I've got on this upper leg of the ladder, and this is the smaller lower leg. And why I've got spin numbers here, I will try to explain you in the following. Okay? First part. So I highlight that indeed interaction here may play a huge role and lead to universal physics, and actually indeed push this logic to the extreme and really simulate this kind of experiment and really measuring voltages. And what you will have to do, and I will come to back this later, actually is to apply a transverse electric field just to compensate the polarization. In such a case, you can define a resistivity. I will come through all this notion in the following, and really test actually that you really measure the density of carriers in strongly correlated regime where there are no well-defined particle carriers. Okay? These are not Fermi liquids, these are Lattinger liquid, but this is many words. I will come to all the details on the following. Okay? Cool. Okay. So just to agree on what is the Hall effect, I don't want to insult anybody in this audience here, but I need to just fix some concepts and why we are actually still interested. I'm not speaking about quantum Hall effect here, but really the classical effect. The story is very well known. You drive a current, there is a magnetic field which is perpendicular, particle bends, there is an electric field which is essentially compensating this Lorentz force. You just do a back on the envelope calculation. You just want to envelope these forces. So you've got a transverse electric field. And you can get interested about the ratio with the current, longitudinal current. This defines for you a Hall resistivity or resistance. And essentially what you get if you divide by the magnetic field, you just get this very, very nice relation that is essentially telling you that the Hall constant, namely the resistivity divided by the Hall by the field, measures the number and the signs of the current. Okay? Nobody shouts here, okay? And I think you should, because this is a calculation which is done in pure vacuum. And there is no reason why you should work in a metal, no? I'm not neglecting at all the many body interactions between particles. There is a lattice, there is disorder. How is it possible these sort of disappear completely for this relation? Okay? There's nothing trivial about that, okay? And so let me just say why we believe it works, from a sort of very, I don't want to, okay, I know that I'm legislated, but I have got all the possible respect for this book, but let's do a very naive analysis, Boltzmann, okay? So what you have to do if you really want to be serious and calculate the Hall conductivity of metals, and this is our research program, essentially you want to calculate conductivities, essentially, what is the reaction of the current to an applied electric field? Of course, I've got longitudinal reaction. This is just the longitudinal conductivity. And then I've got the transverse component, which is telling me indeed about the transverse that response that I get. This is what is called the Hall conductivity. Just a caveat, meaning in linear response, what you have to do is to invert. If you want to get information about the resistivity, the resistivity of metals, you cannot calculate that right away. You have to inverse this matrix, okay? It's a 2x2 matrix. It's not the most complex problem in the world, but these are very complicated objects in terms of their analytic behavior, in terms of frequency and so on. I can answer to questions about it. But okay, meaning if you want to know what, from a Kubo perspective, the Hall resistivity is given by this expression, where you have got indeed the transverse, the Hall component, divided by the product between the longitudinal conductivities along the x and y direction, plus the square of the Hall conductivity. Now we're making weak magnetic field approximation, so we assume essentially that this is just proportional to the applied magnetic field, so I can forget about this step. And what I'm interested about, actually, from a standard Kubo point of view, the Hall response is just the ratio between the Hall conductivity divided by the product of two longitudinal conductivities. Okay? Let's do standard Drude adapted band theory calculation so I can get some fun and actually calculate all these quantities. I'm sorry, it's a little bit small, but I don't want to enter too much in the details. All the aim here, okay, I think everybody knows this expression here, the just Drude longitudinal conductivity just depends on the density of carriers times the scattering time, okay? What is interesting about the Hall response that I think is a point which is not much stress, I think, in our classes, is that it's already something which is even not in the topological regime, if you want, is measuring geometrical properties of the band structure. Essentially, if I look at this expression, actually it just involves what is the so-called the inverse band tensor, which is just second derivative, is the curvature of the band, okay, in band theory. And why it works actually from a very, very naive perspective, because of course, in most conductors, you can essentially approximate bands where they cross the Fermi energy, and depending indeed on the curvature, meaning you can do this sort of a positive curvature approximation. So it's always as if particles were propagating in the vacuum because they behave like parabola, essentially. I can always do this parabolic approximation. And but it can change sign, okay? What I want to make stress about that all this relies on the fact that you have got quasi-particles, namely electron, which scatter with each other. They are well defined. And also let you wonder that indeed their conductivity depends on the square of the scattering time, but as soon as you take this ratio, it just flips up, disappears, okay? Which is remarkable. Okay, this works as long as you have got a normal conductor. The main point, which is, I think, completely open, that of course this goes completely to hell, or it doesn't work anymore as soon as you destroy this quasi-particle and you switch towards strongly correlated conductors, okay? So the main aim in which I think this work has to be placed, even if you want to forget about cold atoms, quantum simulation, and so on and so forth, this is somehow my sort of propaganda message, with all the respect that I have, that I think there is still a huge open problem to understand when I've got a strongly correlated material and I do a whole measurement, what do I measure? Which kind of information I get from the system? Do I measure my, for instance, there is, okay. And here I've got two examples. I can have zillions of examples. So for experts also about the bad metal, what does it mean, the whole response of a bad metal, where you have got scattering time, which is much smaller. So I'm just using ergonomic. Here, what does it mean, all response? I think I don't have any answer. Let me give you two examples here, okay, which are very, very famous, and they are essentially just understood. This is an example, for instance, about all response of organics material. This is called Beshkard salts. I don't want to, they've got some sort of complicated molecular structure, but what you just have to get back from this image is that they are very anisotropic, right? They are very unidimensional-like systems. And indeed, you can think about this system like sort of one-dimensional system which are weakly coupled. So what you have to know, I don't want to enter details here, in 1D interaction always destroy the Fermi liquid. They give rise of a new phase which is called the Lattinger liquid, which is a full field in itself. And the hallmark of Lattinger liquid is all quantities actually behave as power laws in terms of energy, which depend on interactions. And indeed, if you do the whole measurement as a function of temperature, this is what people actually measure. Namely, if you see here, you have got a sort of power law, which is well fitted by this kind of exponent. The point is that as you lower the temperature, hopping between this one-dimensional system becomes more and more coherent. So you lose the 1D behavior of the character, and you have got this dip. This peak, sorry, that is completely theoretical puzzle. And even I think theoretically, meaning doing calculation in 2D with systems which are strongly correlated of all these Kubo conductivities that I was showing before, hard, okay? Really, really hard. And on the right, is the usual suspect. This is a cuprate, so it's an ITC superconductor. So essentially, I'm asking you to calculate the whole response of the Hubbard model. It's not easy. So we don't even manage to hear about the ground state, so a little bit. And here, what I'm showing you is indeed all measurement where you kill superconductivity by applying a huge magnetic field. Okay, many Teslas. Here you kill superconductivity, so you can do all measurement. And you see here you have got essentially many phases. Indeed, you have got a very low. This is the doping. Okay, here you are going away from half filling where you have got an insulator. So you dope the system. Indeed, you see that you have got this is the inverse of the resistivity. So nice all behavior. Charge density wave sets in, the whole changes sign, and nobody knows why. It has nothing to do with the sort of measured band structure. Then you have the closing of the pseudo gap, and essentially transition to a new regime that also remains completely unexplained. Okay, so if there are theories in the room that I think to believe the case, there is an over problem there. Feel free to jump. Okay, and of course there is the second mean just for making everybody happy. So of course there is the second big. Yes.
Your last example about the ITC superconductor somehow is failing with what you said in the previous slide that we need to have a normal metal. So even in normal phase, an ITC superconductor is not a traditional metal. It's more a ceramic material. So why then to use this as an example of place where the whole conductivity does not work if I don't have a traditional metal?
Yeah, but the point is that then the question is, what is then the old response of a non-conventional metal?
Okay, but again, this is mainly a superconductor when it's at a low temperature, but when you are not at low temperature, it's a strange object. So it's far away from being considered a metal.
Yeah, but conventional metals, meaning a high temperature, still behaves like conventional metals. I don't.
Can you consider a high TC superconductor a conventional metal at a high temperature?
Not in this intermediate doping regime. You've got the strange metal there.
Okay, so we can discuss it.
No,
No, the point is that don't worry. Go ahead.
I always worry.
Well, while I agree with the first case, I don't think that the second case is really fitting to say that the whole response does not fit for this system.
There is no theory here. That can explain this.
Wait, it's not important.
Okay. Okay. We discuss it later. But okay, and then there is the second, maybe much more conventionally exciting case when indeed I've got insulator that still can have a null conductivity, so longitudinal conductivity goes away, and then there is the very nice topological object that I think many of you in this room are interested about. And of course, here are many puzzles about, for instance, the fractional quantum Hall effect, the fact that you can get exotic fractions, and so many open questions, okay? Coming from the conmat way of the world. This somehow motivated a huge industry to sort of try to get cleaner systems, which are much more under control, where we can explore this physics, okay? And my point now is to make you, maybe that you're not aware about those, a small review of what people do. I think this is the most important stuff, and how we inscribe ourselves inside this big effort of all together. So there have been many simulations which aimed indeed at engineering. These many pictures, I will go through some of those in the following. In engineering lattices, where you have got essentially a sort of flux which is threading the plaquettes, and highlight topological or just orbital effects, namely that if you go in this direction, there is a force which is telling you, no, listen, go a little bit across this transverse direction. This is an old story, started essentially in 2019, and this is quite evolving. And so far, I think the most remarkable results have been figured out with bosons for multiple reasons, because to some extent, bosons can condensate. So this is the example here. So they really give you access to a big wave function that you can measure massively. And but still, both condensate are not so interacting, and indeed, for highlight correlations effect, so far in the bosonic literature, the state of the art is here, is up to 3 bosons interacting with each other. So it's something very far to Maribor. This is just what, let me be more specific, because we are dealing here with atoms, neutral matter. So how can I engineer magnetic field? And I think really here, the only limit here is your imagination. There are many strategies. One, for instance, is Floquet engineering. So here is an experiment very recent by Monica Adelsburger. So we were speaking about similar stuff just this morning. So I think this is relevant. I'm happy to have put it here, but I did it before we spoke. Okay. So here you have got essentially 3 lasers, okay? That they are, when they interfere with each other, they are just giving up a honeycomb lattice, okay? Atoms tends to sit either on the deep or the top of this, or the potential provide the stationary potential. You can modulate in time these lasers, and essentially what this image is telling to you essentially that you can chirally switch on and off these hoppings between this and this link between 1/3 of the period, then you switch to the left, and then you switch again to the left. Okay, this is a way to engineer chirality in the system. Okay, so in the rotating frame, this really looks like you are putting a flux essentially inside these brackets. And you can start testing stuff that things make sense. So for instance, in this experiment, what the group of Monica did, you prepare a Bose condensate here you dig a hole, so here is real vacuum, and you let evolve, and you see that essentially the condensate evolves along the edges, and you have got a direct imaging of these edges in real space, okay? This is stuff that now there are news, but indeed, this is stuff that in condensed matter was really science fiction until some years ago. And there was also like to test that indeed, this just opens other question, because here we are dealing with bosons, so other kind of regimes question and so on. And just to convince you a little bit more, here you can also change the phase of this drive, so to go from one kinarity to the other, and of course, you have got time reversal of this dynamic. So the blue is in one sense and the red is in another sense. You can change the shape of the border, and you always have walls along the border. Everything makes sense, but this is just single particle physics. With all the respect for single particle physics. But to move to many body, just to tell you also what is the state of the art and how difficult it is, you can, for instance, again, engineer these lattices. Here they have got slightly different strategy to engineer the flux. They shake, so they essentially move a different one-dimensional layer like this, and this essentially modulates the hopping locally. And if you are very, very clever about these phases, you can essentially generate also a flux here. And here what they did also was a sort of conductivity measurement, but through playing the trick of the thermodynamic relation with the Streda formula. Okay, the Streda formula is essentially telling you that if I change the magnetic field spreading to the system, I change the filling of the system, and this is essentially directly related to the conductivity. And in topologically interesting regime, this gives you actually a quantized universal number, which is the Chen number. And in this specific case, this bosons is 1/2. And okay, this is the best that they could get. Essentially, as a function of the flux, they measure the local density in the middle with 3 particles on a 4x4 lattice. So experiment still need to be improved. Okay, definitely. And as you see, indeed, they have got stuff which is roughly consistent with that. Okay. Bottoms. For the people interested about condensed matter, okay, you have got also, and this is also to give you a little bit the flavor of the richness of the field of quantum simulation. We are really getting to the stage where we don't care anymore about the specific platform we are using. Here I'm essentially showing you the same physics, but on a superconducting chip. This is essentially what you see from over is a bunch of circuits. These are transmons, so these are just a superconducting circuit coupled to each other, where you can essentially limit single particle excitation and indeed engineer the coupling. And you can do spectroscopy and just measure the band structure as a function of the flux. And this is what you get. And it is also a funny story, and then I will get maybe to my stuff. I introduce you this paper. This paper has been exactly rewritten, word by word, almost by the group of Yang Wei Pan, but on a superconducting chip of 4x4. Here is the same measurement. It's the same title. They just change ultracold atoms with interacting photons. Okay. So very, very mature field of quantum simulation. Okay, so this was a long introduction, but I think this was sort of obliged for this kind of audience to get you into the field. And I think what we did here in this kind of experiment was, the prediction was essentially studying again a one-dimensional system, two-dimensional system, where particles propagate with amplitude x and ty. There is a flux in the system. I have to convince you how I get the flux, why I've got spin here. And there is interaction, which is very, very particular kind when particles sit on the same rung of this leg, of this ladder. So this is essentially an instance of the Alper-Hofstetter model, and the observable we will focus about is indeed, again, you have got a current, the system polarizes, and we'll be studying in the first place, indeed, the polarization over the current. I will call this the Hall imbalance. So, okay. Different system, you motivate different quantities, please.
Sorry to interrupt.
No problem.
I had this doubt on the beginning. Like you're talking about Hall response in a 2D ladder. Now, for me, the whole quantum Hall effect is essentially a transport phenomenon. So how do you have there like first percolation and then disorder? I don't understand in your physical system.
Let's agree first on the fact.
Or disorder there.
Allora, I'm not focusing on the quantum regime, I'm just looking at the Hall effect of a conductor. Okay?
And then only disorder. Disorder.
I don't have disorder here, it's extremely clean.
Why? Okay, then maybe.
Why, then the question is why
Why don't you need disorder here?
why don't you need disorder here? No, indeed, I'm studying all effects in extremely clean systems, but I want just to focus on the effect of interaction on the whole response of a ballistic conductor, if you want.
It doesn't have a real electric field, it's something different, no?
No, it's just, yeah, you just modulate, you just tilt the potential as a function of space, which is just the equivalent of the electric field, if you want. But I'm not sure to get to the question, really.
I'm trying to make the connection between the whole bar that you showed at the beginning, where you have disorder, and you lower the temperature and you go into the, you said now that you don't not focusing on the quantum for routine, but if you lower the temperature, then you have percolation effects, and that you can also have a high temperature and your physical system here where you have this.
Okay. Let me maybe refocus the question because maybe on this I was not enough. Me, I want to study plainly the effects of interactions, many body interactions, strictly, on the whole response of a conductor. So the effects of disorder on this response are also important, very, very important, but I cannot solve all the problem at the time. My focus is to understand how interaction impact on the whole response of a conductor.
And it's all response because you are putting this
for me, I've got
magnetic gauge fields.
Yeah.
Get this let's say this shift of the trajectories. Right?
Exactly. Me, I call all effect, okay, from a classical quantum here, the limit fades, but for me, all effect is transverse response. I've got longitudinal current, and because of the all effect, I trigger a transverse response. And this polarization, if you want, okay, the system polarizes, but this polarization varies in time. So the derivative of this is just the transverse current. So in the end, everything is related. Does it answer your question?
Almost.
Okay, I move on. And okay, first of all, I have to convince you how I can engineer a flux in this kind of systems, and here is also quite complicated and quite give you a little bit the flavor. What I'm here using is essentially ytterbium, which is a fermion, which is an atom with a huge internal spin, 5 halves, and it is confined in a lot of tubes, which is essentially one-dimensional. Okay. And what I can do, I can essentially liaison the system and induce transition between these internal states. Okay, so the system physically is 1D. Okay, the physical dimension is 1D. Now I can induce transition between these internal states, and I can measure I can prepare all the atoms in the 5-half state, induce the transition. These are just Rabi oscillation if you want. And if I want to measure how many atoms, for instance, flipped to another spins, to another internal spin, internal degrees of freedom, nuclear spin, I just have to do a standard Stern-Gerlach experiment. So I just expand the cloud in a gradient of magnetic field and I just measure essentially spatial separation. This is what you see here. Okay. And okay, yeah, what you can also do actually is to put this sort of transitional lasers at some angle. So the rate essentially of such transition will depend on space. And this essentially will modulate such transition with a phase, whether I'm in this position or in this position. So I can start thinking about essentially the internal spin degree of freedom as an additional spatial synthetic dimension. This is how people think about it. And I call it Y, okay? So this axis is spin. But as I can induce hopping between spin, which is transverse to the current, I call it essentially the Y direction, okay? This is very important. Okay, hope everybody got this point. So if I want to measure polarization, what you see here essentially is just the difference of the internal population of the atom of along this one-dimensional line. Okay. Okay, cool. And just to give you a hint, maybe these are also systems you are not used to. So this is the simulator, if you want. This is how the system looks like. The gas is confined here inside this small chamber. And when people come to you and tell you, listen, a quantum simulation, I have just to turn a button to change all the parameters of the Hamiltonian, you have to change this full thing. So it's really a big pain for the people which work on that, but okay. And again, so also final experiment, also just to get to the end of the story, you can also, people, the group of Jean Dalibard and Nassim Bene, in fact, in Paris also, they played the same game for an atom with a huge number of internal level, is boson again, dysprosium. And here you can really see the whole drift, right? So you prepare all the states in the lowest spin, you apply a force, and you play by playing exactly the same thing of Raman detuning, you essentially see that the particle drift from one wedge to the other by applying a force. So this is really also a direct image. So how much time? This was very long introduction. So
Yeah, it's noon. So
okay, yeah, it's okay. So I think now I just want to enter to the details of what we did, show that we measured this stuff and highlight it. But my main aim here was really to introduce to this kind of experiment and questions. So again, what we did was very different, right? So indeed, we are not measuring anything which is stationary. And what I want to show now that many features of the Hall effect that are used from condensed matter physics, they also show up in completely unrelated settings. So here again, as I told you, I prepared the system at equilibrium. Let's just do an easy non-interacting analysis. So I just take non-interacting fermions on an opera Hamiltonian and just make this quench. So I prepare the system at equilibrium and I tilt it. Okay? What I expect is that the current will flow to the system. So the system is accelerated, so the current flows and increases over time. This is very non-universal. It depends on all the details of the problem, how much I tilt and so on and so forth. And on the same time, and this is really a signature of the Hall effect, a polarization builds in the system. So particle starts accumulating with different weights on the upper and lower leg. This is the difference of population between the particle which sit here and which sit here. Now, what is quite interesting is if even though this stuff evolves in time, if you look at the ratio between the two, so Py over Jx, what I've dubbed the Hall response, this response actually gets quite stationary, a very short time, and we could actually calculate it. So in a regime where Ty is much larger than Tx.
sorry, what is tau in this?
Tau is time.
Okay.
It's time, no? Is this just time evolution? This is just non-interacting analysis. So for instance, we studied the problem, for instance, with two legs and band as a function. For me, the regime in which we want to focus that I find also quite interesting is the fact that at very large tunneling, this is the band structure of the model. For instance, for very weak, I've got two legs, so I've got two bands. A very weak tunneling, actually, I've got the chemical potential typically which cross along all the two bands. If I increase the tunneling, essentially the chemical potential which just cross one band. So this is also quite an interesting regime from the theoretical point of view because I've got effectively a one-dimensional system, so particles moving to the left and to the right, but still I have an Hall response, okay? And this regime here is characterized by essentially what we call, I will come on the universality later, by a value which really does not depend on many of the details of the system. For instance, the number of carriers is not appearing here. The strength of the drive, nothing is appearing there, only some microscopic values.
Question.
Yes?
In the band structure, the color code.
Sorry. The color code. Sorry, I've got actually. Okay. Let's construct the band structure from scratch. Here, let's imagine that the two chains are uncoupled. So I've got two one-dimensional systems, two cosinuses. Blue is the lower leg and green is the upper leg. Okay. Then they are still uncoupled, but I played the artificial game to insert a flux, so they shift in momentum, right? Because if they jump from one to the other, and then if I couple them and just open a gap in the middle. So, and of course, if you go, okay, so this is what you see here, right? You are just the more you increase the coupling, the more you gap these two bands each other, and this really looks like spin orbit models, like for 1D. That you is just the same calculation. I mean, and indeed, if you go to the left, you have got a flavor which is instead of spin here you replace by leg, spatial dimension to convert to the language. So left you will tend essentially to propagate more on one edge than the other, essentially. And this is why you have got an Hall response in 1D. I really had to convince people about this fact that you can study Hall effects in effectively purely one-dimensional people. People were not believing that, but it's true.
1D or classic 1D? is 1D or quasi 1D?
This from
That's for sure, but your system is quasi 1D.
yeah, is embedded in a higher. Of course, you need some orbital flavor, otherwise you cannot see up and down. But many people would expect, okay, in this regime, if you have got only one conduction point, no effect. Okay, it's not so trivial inside.
Sorry, but if you have Ty, this means that tunneling between the other direction is not 1D, no?
No, it's not purely 1D. It's effectively 1D. No, of course. I have to have two. No. Sorry. I'm stretching.
You define a phase, and then you have only one propagation direction.
Yeah. Here I've got only. You see, I've got only 1 degree of freedom, which is a cut. It's more important. If you want, you can, without magnetic field, you have got antisymmetric and symmetric sector between the two legs, bonding and anti-bonding. You can speak it as you wish, and you confine yourself to the bonding sector. Okay, but here you can claim, listen, this depends on detail. The first surprise, and this was our numerical calculation, is that we ran the MRG, we calculated how this whole effect happens in the presence of interactions, and by increasing interaction, no matter the fillings, no matter the initial filling of the band, as long as you were below one filling, what you would see is a sharp transition to a value which was always the same.
These interactions are between the
legs. And this was physically motivated. Sorry, I didn't go really to this point. So you understand very well that particles interact only if they are on the same side. So here in this picture, you don't have nearest neighbor in this direction, but you have got putatively long range if I was going to do the infinite size limit along the synthetic image. So this is why I had to choose. But this phenomenon is generic. I wanted to stress that. And what was very, very important to pinpoint for us, meaning that this was really an exquisite non-perturbative many-body effect. Because you could have done mean field, for instance, right, of the interactions, and mean field, what it does between these two bands, gives you a little bit the quantitative. Mean field, what it does is just normalizing the coupling between the two bands, because it's an interaction along the transverse direction. So it would open indeed a gap, and it will give you essentially a tendency toward the 1D. But if you look at the equation, this would also tell you at the same time that the more you increase the coupling between the two legs, the more you would suppress this response. Okay? And this is 100% not we saw here. Okay? 100% not. And actually what is happening is a little bit more involved, essentially, that you have got an SU2, okay.
Can you go back one slide?
Yes.
No, the other. Yeah, so here, attractive, okay, no, I wanted to understand because you should have a whole effect without interactions as well, right?
Yeah, of course. And this is here.
But it's not quantized.
No, because these are all regimes where the coupling between the two legs is weakly. So you are always in a regime where you have got where the Fermi level crosses the two bands.
So if you would increase Ty, then you would.
This is this plot. But Ty increasing mean also you see a Ty here.
Yeah.
This goes down, this is suppressing.
Okay.
And the more you decouple,
the universal value depends on the. Okay.
Yeah, but here, no, indeed, here Ty is fixed, and you increase interaction, you get to something constant. Okay.
And this quantization, it depends on.
It depends on Ty 100%. Okay. So no universality, nothing universal at this stage. Okay. I want to agree with you on a different definition on the following. And this is the next slide, actually. But what is happening actually is the following, is that if you put yourself in the limit of 0 magnetic field, what you see that the interaction is SU2 symmetric, so you can rotate to the bonding and anti-bonding state. And essentially this creates, you don't want interactions, to kill this term at U infinity, you want to depopulate completely the upper band. So essentially you have got a transfer of particle from the upper band to the lower band. So you increase the Fermi level, but you MPT the upper one, and you stabilize a one-dimensional metal, an effectively one-dimensional metal, which means for me only one flavor for the charge current. Okay, that I've got spatial structure, but I hope this okay, good. Why universal? because we did other calculation, and if instead of just looking at the polarization, which is still very robust quantity, because again, this does not depend on the drive, on the density of many things, neither the interaction, a very, very strong interaction. But if you were able to indeed to apply a transverse field, which is an electric field, such that you kill the polarization, I can show, and this is a part of the mysterious part, that you would get indeed this density of carrier measurement very resistant. And this, I would claim that this universal result is not quantized, but it does not depend on whatsoever else than the density of carrier. Okay? So, but long story short, we managed to show that in a one-dimensional system, which is strongly correlated because it's a Rattinger liquid, I've got strong interaction, still I can restore this law by pushing the interactions very, very strong. Okay? And this is not mean field effect, it's really exquisite many-body. Okay? And now I want to show that it's robust, and to show that it's robust, actually, we show that you can see all this in an experiment that is completely uncontrolled. Okay? And this is, I hope not to rush too much, there were questions, but this name is not many slides. Please be patient. I know that you have to go for lunch.
You have time. Yeah. You have some.
Me, I had some biscuit before coming here, but I think it's not the case of everybody. But I don't know, yeah, there are people which get angry and aggressive when they have to eat, so please don't. So, this is the experiment, okay? I tried to give you the basics of the experiment, so let's look how far it is from what I was telling you before. They really did what I told you, like they prepared the system, and they quench it, and they measure the momentum distribution, and from that they can reconstruct the curve. What they get, this is the data, is this very, very nasty curve, okay? Where you indeed see that at the beginning, essentially, the current increases as a function of time. This is totally expected. What you see that is also drop. This is a mixture which is very, very difficult to infer by the fact that the system has got finite size. So it's confined in a parabolic potential. So at some moment, the current hits the end of the sample and gets struck back. Also, to get decent signal-to-noise ratio, they had to give a very, very strong kick, meaning here the quench, the electric field that they applied is of the order of the longitudinal hopping itself. So for people from condensed matter, you really have got stark oscillation. So there is also a little bit of that. But what was very important that no matter how, of course, going with that, you also have a polarization which is building up. We tested that if you change the sign of the magnetic field, the polarization changes sign, the current doesn't move, so a lot of sense. And if you take the ratio between the two, no matter how complicated this curve is, and I can really tell you that there were many complications, this is averaging the currents among many, many, many tubes. This I didn't tell you maybe before, but here they are just measuring order of 1,000 of tubes, all with different density and occupancies on site, and the average among all of them. And still, you take the ratio, you are very, very, very strongly out of equilibrium. Actually, here the temperature was also very, very far from zero. It was of the order of half of the hopping itself. And still, you take the ratio between the two, and okay, meaning you don't see much, but you approach for very, very strong interaction very, very closely to this value that we calculated, that I was giving you before, and there is no any fitting parameter there. Okay? Okay, this is not enough to convince anybody, so let me do a much more systematic study as a function of the system parameter. So we just look at the average, we just average over time and just look at the behavior of this quantity as a function of all the parameters. Yeah. I average over the period of measurement. So first example, first things first, you look as a function of this all response as a function of the strength of the coupling between the two legs. So just to convince that everything makes sense, of course, at zero coupling, you don't have any all response. Okay, this makes a lot of sense. Strong interaction, you push Ty, and indeed what you get, if you just renormalize by Ty, you take this factor away, this suppression, you really get more or less clean, this is on the eyes of the people, to the value we predicted. So it really fits completely with this without any fitting parameter, which I find something pretty impressive. And this is also quite difficult to be compared with theory, so averaging all these tubes and so on. Of course, we cannot do calculation of finite temperatures because there is no efficient algorithm to calculate transport, even in 1D at finite temperature. So you can compare, if you want, with the Mergimat at 0 temperature. So this is the red line here. A very, very strong hopping, you agree. A low hopping, there are deviation, and these are mean field analysis, on top of which we put some sort of temperature just to explain this deviation over here. I will get it for the question. And the most interesting curve indeed was the fact that as a function of interactions, you would really, really stabilize this sort of value that was completely predicted by theory. Okay? No fitting parameter. So again, this was the first experiment. We showed up some non-trivial interaction, many body effects of fermions on the response of non-interacting, interacting correlated effect. And again, this discrepancy, and this was the huge fight with the referees, because here in quantum simulation business, people want to see always all the data reproduced by theory. We had to explain to them that here was the typical hard-to-compute regime where we couldn't produce any sensible theory to fit this stuff, because this is really the regime where interactions, hopping, temperatures were all of the same order. And I'm not aware of any decent algorithm which could reproduce this data. It's out of equilibrium, 200 sites, 40 particles, this kind of math for the specialists, okay?
So how do you link it to the density?
There it is. Alors, I show you before the measurement and then I tell you how I link it. Okay? I think this is the interesting question because it is where I'm totally confused and it is open. But I've got some signs. We did, just to make it how much time do I have?
10 minutes with questions. So
okay,
maybe
it's okay.
five.
No, it's 3 slides. Huh? I did it, I was very long in the introduction, but I think it was really needed. Yeah, so. Okay, we did just to confirm. Now we sort of apply this transverse magnetic field. So essentially, this was a very, very heavy measurement for the experimentalists. So you apply a transverse field in such a way to kill this polarization. This defines you. This defines you somehow the Hall effect. And this is really reproducing somehow this picture here. Yeah? You're looking for the electric field which compensates for the Lorentz force and which doesn't trigger for the polarization. And as a function of so this is the experiment, so this is what appeared last year. And indeed, what you have to do indeed is to check as a function of this electric field that the polarization response for different particle numbers. So this is what we were checking. The current, the voltage, you take the ratio between the two, you get the inverse resistivity, and without any fitting parameter, this just fits with the number of particles over the flux, which is, here we put a tangent because we are not a very, very small field, okay? So, but of course, a weak field is just the field. And this we did for 2 and 3 legs, so we also added a leg. And you see, I mean, the agreement is, I find it pretty decent. There is really no fitting parameter here. It is just a plain Hall effect without any adjustment. Okay, so indeed, this was really the show that you could measure the Hall response of a conductor, which is strongly correlated and still obeys this rule. So the question now, okay, and this is what we did essentially. I don't need to repeat the results. But indeed, why does it work? We scratch a lot our head because here all these arguments of, for instance, Lorentz invariance and so on and so forth that you typically apply, they don't work. Because you've got huge temperature, you really don't, you don't have a, you don't have an invariance with this Galilean boost. Sorry for the technician. But what I could show, and sorry, this is a little bit technical slide, but I leave you with that, is that if you are in one single band and you do perturbation theory in the hopping, in the coupling, in the strong coupling limit of Ty, you can do perturbation theory in 1 over Ty. You can relate a very important relation between the polarization, the current which flows in the system, and the density of carrier in the presence of an electric field and the flux. And this is completely agnostic about the driving protocol. So it's really, I don't care how you drive this current. It's always true, as long as you're in the single band limit. And if there is a factor for the polarization, which depends on the band structure of the model. But if you impose that this polarization is 0, you get this, the polarization is 0. This is just converted in the experimental relevant quantities. But what you get indeed that the ratio between the field that you have to apply to have Py equal to 0 over the current that flows in the system doesn't depend. It depends only on the field and the number of couplings. Okay? And indeed, this is all the big question is why. Meaning I can really show that, but whether there is some sort of deeper argument there, for me is open problem. Okay? And maybe reconnecting to one of the questions about disorder that there was before. Okay? I think all what I've showed you so far is in the presence, the only scattering mechanism is interactions. Okay? But indeed, you want really to approach really diffusive regimes where the current is diffusive, okay? And this is the big open problem in out of equilibrium quantum transport so far, okay? So there are very few techniques on which you can rely to move on. I took a lot of time, I had 10 minutes of slides explaining how we are doing progress on that, but I think I have to skip that. Huh? So I told you that it was modulable, so it's okay. But I need to show you some slides about where I'm from academically, so this is stuff that we can discuss this afternoon. So I'm from Grenoble. I don't know whether you know this town. This is Grenoble is in southeast of the Alps. It's called the capital of the Alps, but this is just French propaganda probably. And I'm registered, right? I'm recorded. Good. Oh my God. So this is the Alps, which end up from the Mont Blanc. I really see it from my window in the morning when there is not many clouds. It doesn't look, of course, always like this, but now if you look at the mountains, it's more or less faithful representation of the situation. This is the closest key piece, is 45 minutes. And this is the town, the old town, and this is all the scientific campus. And we are dispatched all there. I think I was here, Adolfo, before betraying us, was somehow here, I guess, you know? There is a huge synchrotron facility, this big ring, and of course, when it is too warm in summer, people are crazy, so they just sleep here and they come to work in a tent, and they come work in the morning. Indeed, this is a picture of me from this mountain. And indeed, there is a huge activity also there in building out quantum devices. We are pioneering, this I really just to advertise in 1 second for the Mont Condensed. We really managed to get strong coupling between a single spin and photons trapped in a microwave resonator. And this is really opening the way to do circuit QED experiment with spins, which are pure two-level system. And there was, for who was doing science, there was a Nobel last year about making this possible, but they had many levels, superconducting circuits, and we killed many of these levels. So it's extremely promising, exciting. I can tell you about it if you're more curious about. The reason I'm here, I don't know whether you take interns, but I guess there are two very entitled persons to give a talk about the story, if you want. Don't kill me, Sergi, but but I did your name, so I think we have got very nice tool based on ZX to investigate topological phases. This is why I'm here today, and thank you for your attention.
So, yeah, we have time for a few questions, and also if the people in the Zoom have questions, I can read it out loud. But first we take in the actual room. Yeah, Dario.
If you go to the limit in which you consider more internal degree of freedom of the system, would you deviate from this 1/n behavior, or would you are expecting to respect it?
It's a weird limit because here I'm doing a lot of, no, I have to stay in the single band limit. But of course, the more you add degrees of freedom, I'm densifying the band spectrum. Like, and then
you'll be in the single band limit in that case.
I
mean, if you have many parallel wires,
yes,
you could still tune the system to be just in a
but then I have to go to lower and lower densities, right? Because I don't have blackboard here, but I've got, if I had a third one.
You have a whiteboard.
You have
over there. I do it without magnetic field, but oops.
Take a few. I would take a few.
Yeah, indeed. I've got two. If I insert a third leg, it will appear here.
Yeah.
So indeed, the relevant, and in the infinite limit, this will be completely become dense because you are 2D. Okay. So indeed, I think one of the big surprise from all this work is that you can still see all this physics that it is in the 2D limit, in the effective one-dimensional limit. This was a surprise. This said, indeed, this become more stringent, but you can still do that. It works the same. So all the stuff that I told you generalizes to arbitrary number of legs. You can also take the opposite limit of one-dimensional systems, which are extremely weakly coupled. Okay, which has nothing to do with this, because I start from a bunch of linearized band structure coupled to each other. Also in that limit, you can find, if you start from Latinger liquid, also there you find the 1/n. There are a lot of observations, but I think the research is completely open. And what is the effect of interaction here, for instance, if I'm with an extensive number of bands, and I put huge interactions, local, interactions tends to kill mobility. So as a matter of fact, they will gap the system in some way. And if you manage to stabilize a metal, maybe you will get still this strongly correlated behavior. But this is very, very difficult to show.
This would be more similar to the case of this strange polymer you are using as a showcase to say that in the active system, things are not following the classical order.
Exactly. But the point is that if you do, this I was saying, because you can do calculation if you take 1D system which are weakly coupled, then you can do perturbation theory in the coupling. But the point is that as you lower the system, you are not perturbative in this term anymore. So hello, find something else. Open, totally open.
Actually, I have a related question. So in your plot of like that plot, but you also had a 3-leg ladder, which looks like a little bit lower. And so I was wondering the same thing. If you keep adding ladders, the interaction is actually long range, right? You said.
Yeah.
So do you expect this thing to hold? I mean, you already answered. So
with 3 legs, I can say something essential.
Could it be that you're not? So is it for the 3-ladder case? Are you still in the 1D one band regime?
Yeah, for 3 I've got numerics which support me. Okay. Then I could speculate about, but as I cannot be benchmarked by any kind of indeed, what would say the theory is that is long range, so the symmetric mode would be stabilized by this. Then, now in many-body theory, if you don't have any numerics that supports you, I can say yes, maybe, but okay.
Okay, I have another question, but maybe if there's anyone that is okay, one I'm gonna take my so you seem to not care about the density, like the filling, let's say. And they're fermions as far as I understand. So at infinite interaction and a certain densities, don't you get charged the waves or?
No, of course they do.
But then this
no, in all the commensurate limits.
Right. So in some feelings you cannot get this, right?
Exactly. But this typically only the commensurate ones.
Yeah.
No, and this you see, this was hidden in the data, but you get the band insulator becomes the mot insulator. And this you really see at our feeling, for instance, for the 2 legs. It's here. See, there is this white line.
Yeah. Okay.
Our feeling.
Great.
No, everything makes sense. Yeah, and indeed, this is no interaction, so band insulator, and here, okay, there are also things that meaning a particular symmetry at our feeling, when effect is 0, so it changes sign. Yeah, so there are many of these regimes. Yeah, indeed. Yeah.
Okay, if there are no more urgent questions, Michele is still here this afternoon, and maybe tomorrow morning at 10 you have to leave something.
Depending if somebody needs to.
If somebody wants to talk to Michele, let me know and we can arrange it.